Hi, welcome to Quantum Field Theory Lecture 13. So last time we spoke about observables and how to extract the simplest observable from the quantum field theoretical amplitudes, the decay, right? So just a particle sitting there and eventually decaying in a number of final states. We explicitly looked actually at a two-body final state of a decaying particle. So that was already good. We extracted our first physical observable. And now we want to look at a more complex process with two particles in the initial state which scatter with each other. And by scattering, I mean interacting in either an elastic or inelastic way where energy is exchanged and particles could also change their quantum numbers. So incoming and outgoing states are not necessarily the same. Then we call it inelastic interactions. And if they're the same, this is just a deflection, we would call it elastic interactions. So first of all, let's think about what scattering processes are or how to describe them. And the basic observable or the basic ingredient we need is the flux of incoming particles. It's essentially the number of particles that pass through a unit area per unit time. We call it F. And the interaction rate is then given by this F, the flux, times an object that we call sigma, or we denote as sigma and call cross-section. So knowing the flux and measuring the total interaction rate tells us something about this quantity sigma, or if you measure the flux in the differential flux through a solid angle, that means particles that have been deflected at an angle theta. Typically it's phi symmetric, but if particles interact and get deflected into a solid annulus that is reached by a certain angle theta, then we can also measure the differential cross section d sigma. Now let's see what F actually means. It's a number of particles per area per time, but we can multiply, right? So let's have a sketch here. We have an area and a certain number of particles fly through there in a unit time. But now let's take also the length here and see that, well, we take the length to be arbitrary and multiply the numerator by L. So we have here we have an L over T, which is the velocity of particles that come in. And then this L we combine with A to get the volume. So actually the expression didn't change, but we have rewritten the flux in terms of the velocity per volume times the number of particles. And this is a convenient way of writing the flux for later considerations. But still the picture is the same. It's the number of particles that pass through a certain area in a certain time. Now consider the differential transition probability. Remember, we had defined the transition probability as the square of the amplitude, so the sandwich between final and initial states of the scattering matrix squared divided by normalization of the initial states and final states. And then for the differential probability, we have the differential that is also summed over the phase space volume of the final state particles. So this was the expression we derived last time for this differential probability for an interaction. Well, now we have the initial state is not anymore like just it has a relativistic normalization, and it is not a one particle state, but it's a two particle state. So that's what changes here. With respect to the last time, there's only an additional factor of 2e2 of the other particle that comes in. So we have two particle species. And now we have the definition of this differential scattering cross-section, where we have the differential probability divided by unit time by unit flux. Unit in the sense that it's flux per particle. That means that we don't have the n anymore in front. It's just the velocity divided by volume. So we have this dp divided by tf. Okay, so we have also vt in here. So this v gets cancelled by the v in the differential in the unit flux, and the t gets cancelled by this t here. So in the end of the day, what we end up with is the matrix element squared the measure that we need to sum over the phase space of the final particles. And there's we divide by this normalization factor for E1, E2, and their relative velocity. Now, the way we set it up, it's not Lorentz invariant because we had a particular frame where the particles are colliding, where we define this velocity. So we actually are in the laboratory frame, and we can take another special. Let's try to rewrite this expression in the Lorentz invariant way. And to see how to do it, we look at this quantity I and evaluate it in the frame where one of the particles is at rest. We can do that. That's no loss of generality. We just, we see that it's a special case where we can make a good connection to what we just derived. So let's say this quantity I has the form momentum R1, form momentum 2 of the incoming particles dotted into each other squared minus the product of their masses squared. So when the one of the velocities is 0, then we just have the product of the energy squared minus their masses squared. And the one energy E1 is just P1 squared plus M1 squared, and E2 we leave for now like it is, but we actually remember that E2, since the particle is at rest, is just M2, right? So that's why we can replace M2 here by E2 and pull it out of the square root. So we have E2 up front, and then we subtract, this M1 squared minus M1 squared is cancelled, and we just have P1 squared, the free momentum, which is just, now under the square root, the absolute value of the free momentum times E2, and that's the same as the product of E1 times E2 times the difference of the velocities, where we have used this property of the momentum that it's equal to M1 times V1 for P1 times the gamma factor, the Lorentz boost factor, and this M1 divided by the gamma factor is just the energy. So this is E1 times V1, but since V2 we have set to 0, we know that we can also write E1 times V1 minus V2, which allows us to connect to this expression. And in fact, this is a slightly abbreviated derivation, but this holds in general, that this d sigma is equal to a squared d pi n, so the measure for the integration of all final states, and divided by 4I, where this is the generalized Lorentz invariant flux. So we have this Lorentz invariant differential cross-section expression here, which is a useful result. Now we can evaluate it for a two-particle final state, taking the center of mass frame, which is quite convenient for many observations. You remember we had derived last time this expression for the two-particle final state, where this is the final momentum absolute value, this is the initial state energy. And in this picture that we have P1 momentum and P2 coming in, Q1, Q2 momentum going out, we saw that this situation is symmetric around the angle phi, so it's independent of it. So it can only depend on the variable theta here of the scattering angle. So let's write in components how the momenta look. It's P1 is E1 P initial, let's call it the P1 P initial. And P2 is E2 minus P initial, because when they have to sum up to 0 as we are in the center of mass frame. So E1 and Q1 and Q2 also have momenta that have to sum up to 0. We call them Q final and minus Q final, and they have the corresponding energies. Now we don't want to write this clunky notation for the absolute value, so we write this Pi for the absolute value of this free momentum, initial free momentum, and the QF as the absolute value of the final free momentum. Now we said the variable S is defined as the sum of P1 plus P2 squared, This is just E1 plus E2 squared. So it's obviously just total energy of the initial state. And this quantity P1 times P2 squared minus M1 squared times M2 squared, we can explicitly put in the definitions up here. We see that this E1, E2, for two incoming particles, the angle between them is 180 degrees. So we get the cos of this angle is -1. So we get here plus P initial squared minus M1 and 2 squared. We can just multiply everything out. We see that this the mass terms here cancel, and then we can pull out a P initial out of all of these terms and get a P initial squared times this expression. However, we can we find this is nothing else but combining these energies, just E1 squared plus E2 squared, and we see that this is nothing else but E1 plus E2 squared, which is S. And so this I in the center of mass frame is just square root S times the initial momentum. Quite a simple expression. We can now write the explicit formula for the total cross section for the two final state, for the scattering into two final states. We take that the integral over the d phi. One moment, we called it actually d. It's very often also denoted with phi, but we had used the notation d pi, so we should stick to the d pi notation. So what happens, we put in the definition of this measure here, and the integral that remaining runs over the omega. We have the ratio of the final momentum and the square root of s. So we have the final momentum, square root of s, and I here. And now we know what I actually is, and we know, yes, the expression in terms of s. And that means we have a s in the denominator here, and the p initial and the p final. So this total cross section, total cross section, the integral over the omega, and the ratio of the final and initial momentum is here. It's quite important. And then we have the matrix element divided by the total energy squared, ds, and prefactor 64 pi squared, and then this solid angle that measure that we use to integrate over this matrix element, and we'll see a couple of explicit examples. So this is the cross section for a 2-to-2 scattering process in the center of mass frame. This is also quite useful formula to have. Let's look at some explicit examples. For example, let's start with the particle-antiparticle scattering. Just psi bar, psi, and scatters to psi bar, psi, so nothing really changes in the quantum numbers, but yeah, they can exchange energy and momentum, of course. Now we see the diagrams that can play a role. So there are three diagrams. The thing is, they can actually annihilate into a phi particle, and then that phi particle decays again into a psi bar. So that would be a scattering process, even though in the intermediate state, both particles are actually gone. Still, it's just a scattering. But they can also exchange the phi, as we've seen before, in the T channel and in the U channel way. The momentum assignments are basically the same as in the other examples here, at least. And here we have the sum of the momentum going through this internal line, which is the propagator of phi, and we will see how that is actually important later. But we can just evaluate those phi diagrams using our Feynman rules, and we find, of course, the negative I squared, negative iy squared, and the i's from the propagators combined to this factor. And then we have three propagators, one for the S channel, one for the T channel, and one for the U channel here. Now I just want to introduce the so-called Mandelstam variables, and this is the reason why those channels carry the names S, T, and U, or vice versa, who knows. But the physicist Mandelstam has introduced them and used them quite excessively, and they're quite successful and useful for the abbreviations of momentum combinations and in amplitudes. So S is the sum of P1 plus P2 momenta, the initial momenta squared. T is the difference between the initial and the final momentum squared, and U is the difference between the initial and the other final momentum squared, basically corresponding to the sum here, the difference here, or the difference here. They are representing those the momentum exchange in those diagrams. They are Lorentz invariants as their products of four vectors, and they appear here exactly in this propagator. So we could also write this is equal to S, this is equal to T, and this is equal to U. Okay, so this is quite manifest the Lorentz invariant way of writing it. Now we can evaluate it in the center of mass frame and to study a little bit the behavior. And we know the total energy of the system in the center of mass frame is S E1 plus E2 squared, fine. And now let's assume that the initial momentum and the final momentum are spatially are similar, so there is not much of momentum exchanged. Let's call them P. Then we can simplify T and U as just negative 2P squared, 1 minus cosine theta, and the other is negative 2P squared, 1 plus cos theta. So they are really measuring the momentum transfer, while S measures the total energy of the system. And if we also assume that these if we also assume, so we can, yes, we will make another simplifying assumption in a second. So for now, our differential cross-section, d sigma by the omega, is just the matrix element squared, the ratio between the final and initial momenta and the total energy squared. This is fine. And then let's make a further assumption that the momenta, the initial, which are similar to the final momenta, as we said, are given by the mass of the particle psi times its velocity. And the velocity is not large, so it's smaller than the velocity of light, which we express in v is much smaller than 1 in our units. So then we can simplify the total energy just by the sum of their masses. So S would be the total energy squared, just like 4m psi squared. And T and Q would be 0 in that leading order, because here we have a v squared, which we say is a small parameter. So then the amplitude becomes really simple. So this one is just 1 divided by 4m psi squared minus m phi squared minus 2 m phi squared. And we have no theta dependence. And this is an example where we can simply integrate over the solid angle omega d omega, and it gives us 4 pi as we discussed last time. So the total cross section here in this case is just the constant, the matrix element squared here, which is also just a function of the masses, and divided by 64 pi m psi squared. Excellent, yes. So we now have this expression, and what we observe is actually that it's proportional to 1 divided by m psi squared here. And remember that the de Broglie wavelength of a particle is given by 1 divided by its m mass. So the Broglie wavelength of this psi particle is 1 divided by m psi. So the cross section here is just given by the de Broglie wavelength squared, which is physically can be interpreted as really the area, kind of physical area of the particles. And so in this non-relativistic approximation, the behavior of those scattering particles would be roughly similar to two billiard balls scattering off each other, because the total interaction rate would be really just there. So the area which they see from each other from the front. So yeah, for a classical particle, it will be just pi r squared, right? So this is, we have a prefactor times the radius or the diameter squared of this quantum mechanical object, but we don't really see any. The scattering is also totally isotropic. We don't really see any dependence on the theta angle, If we go to larger velocities, then the matrix element would become more complicated. We would have the T and U channel would have the theta dependence, and you would have a more complicated integral over this solid angle that would give us theta dependence in the scattering process. So, but this appears at larger velocities. There's another general observation, okay, that the S channel diagram has a resonance at when this S variable, which corresponds to, if we assume that both particles have the same energy, let's say it has the energy 4e squared, the S variable, when this approaches m phi squared, or when square root S approaches phi, the function here actually diverges. Really, so if this denominator goes to 0, the function diverges, so the amplitude becomes infinite. However, it's not really infinite. One can show that since m phi has a decay probability back into psi psi, for example, psi psi bar, we know that the propagator behaves as k squared minus m phi squared, so here s minus m phi squared, plus I gamma m phi, where gamma is the decay width of the phi particle that we have calculated in the last lecture. So the sigma, the cross section, at when S, or the total energy, approaches m phi squared behaves, this is a small parameter, and the cross section has been dominated by this gamma squared over m phi squared here, and this is called the width of phi as well. And I can just show you why it's called width. So if one does experiments in the laboratory of scattering of those particles, for example, we can plot this cross-section as a function of the energy, total cross-section as a function of the energy, and you will find that this has a shape similar to a bell curve, which has a maximum around the mass of phi. So this is also how particles in the laboratory experiments are often discovered, like the Higgs particle was discovered this way, has a resonance of the interaction cross-section. And this width here corresponds roughly to the width of this distribution here. So the lifetime from the width of the distribution, we can understand what the lifetime is. So for a very long-lived particle, gamma is very short, very small. The decay rate is very small, so this becomes a narrow peak and a very clear pronounced resonance. If we have a very short-lived particle that barely comes into existence and immediately decays, this peak would become more and more smoothed out until it's really hard to call it resonance. This is the case for many resonances or quasi-particles in quantum chromodynamics that are so short-lived that it's really hard to say if they're really particles or just just very loose kind of results of multi-particle interactions. So that at some point, even the definition of a particle becomes fuzzy when the lifetime becomes very short, and also in the sense of resonances, when the resonance is not really a clear bump, but something very very smoothed out. It's really hard to call particles. But this is a very clear indication of particles in the laboratory, and a lot of the particles are really detected as resonances in cross sections. Let me tell you another story about scattering. About 1960s, especially like pre-1968 actually, people were studying scattering of mesons in quantum chromodynamics, and they knew that there were like a lot of the mesons. There's a zoo of these phi fields. You can imagine these phi scalar fields with an index I, and there are like quite many of them. So if they do contribute to these interactions, to scatterings, we can calculate the amplitudes by summing. So what we learned from quantum field theory, we calculate the scatterings by adding T and U channel diagrams. Let's assume that they're just no S channel, but just T and U channel diagrams, and sum over all the mediating particles phi. But the bizarre thing what they measured was that actually the scattering amplitude that described experiments was what the sum over the T-channel diagrams only, that was surprisingly exactly equal to the sum of the U-channel diagrams only, not their total sum and then taking the square, right? This is absolutely distinguishable, and the experiment was clearly saying that that is the reality, not this. So one could doubt like the principle of quantum field theory and quantum mechanics at this point, but actually the resolution came in quite soon that people realized that mesons are not really point-like in this picture. So they are actually excited and much better described by Q-cube quark antiquark pairs that are connected by the string. So the picture here, what we can draw is that the particles that come in, some momenta, are extended one-dimensional objects, and they merge at one point. They interact at one edge, merge in the longer string, move together for a while, and then fall apart into separate strings again. So now, when you think about the momentum flow, it could be described by a flow of momentum exchange that is the T-shaped channel. Sorry, what we were talking about T. The S channel actually, the U channel is basically the same here. So we have the important thing is actually the S channel. I apologize. So what we have here, the picture what we have is either we do this exchange, or we could also assign, so the T and U channel here are basically the same in terms of their topology, but we could also have the S channel exchange where we have a direct flow through the middle of the mediating particles, and this is equivalent, right? So in this picture, the S and T, which is similar in this, is actually equivalent to U here. They are the same. So this topology and those topologies, they can't be really summed, but they are rather a description that is, that can be chosen. So you either choose to do the S channel description or the T channel description here, and they're both equivalent dual descriptions. And that was discovered actually by Gabriele Veneziano, who discovered the so-called Veneziano amplitude that was absolutely ST symmetric and described this interaction. And one can show that this amplitude comes from a scattering of two one-dimensional objects. That was also actually the point in this 1968 when people became interested in the theory of one-dimensional object, the so-called string theory. Okay, now let's try to draw diagrams for particle-particle scatterings in terms of particle-antiparticle interactions. And well, they're basically the same as before, except for the S-channel diagram doesn't exist because particle and particle cannot annihilate. So we only have the T and U channel interactions here. There is no S-channel resonance, important physical difference. And otherwise, the physics in the cross sections will be very similar. Just get rid of the S-channel interactions. The other example is a particle-antiparticle annihilation. So we can have psi bar going to phi, and let's see how that diagram looks. So here we could have incoming antiparticle exchanging the particle itself in the T channel, and then we have the particle coming in that are connected like this, and they're going into two phi particles. So this is a really inelastic process where the psi bar disappears. There's no charge anymore. There are two real chargeless fields phi. It is kind of an analog of the process like E plus, E minus going to two photons. The spins are different, but the charge transfer is the same as in the annihilation of E plus, E minus to two photons. And there's as well a T channel and the U channel diagram. And we can use the Feynman rules to find the propagators with this being T, this being the U variable. And that is evaluated again and do some simplifying assumptions. For example, the velocity, again, the relative velocity is much smaller 1. This is always helpful. And we can also assume that m phi is much larger than m psi. I mean, it has to be smaller than m psi in order for this process to be energetically allowed, but also assume that it's much smaller. Even, let's take it even in 0, that m phi is actually massless. And then with the S, it's the same. The S total energy is just 4m psi squared in the initial state. But S is equal to also to Q1 plus Q2 squared, right? Because the total energy is conserved. The momentum exchange, or the momentum of the final states, is exactly equal and opposite, because we assume that the two particles here annihilate basically at rest with neglect the velocity. So the momenta are 0, so the final momenta of the outgoing phi particles have to cancel exactly. And we'd only have the sum of the energy squared. But since they're massless, this is just the sum of their momenta, final momenta squared. So it's 4 final momentum squared equals to, equals to 4m psi squared. So final momentum has to be exactly equal to m psi of those particles. Fine. And u, p1 minus q1, we can do the analogous calculation and find that's equal to minus psi squared. And so in this diagrams, so for u and s, we get minus psi squared here in the denominator. So we have minus 2, minus 1/2 over 1 divided by 2 psi squared. 1 divided by minus 2 psi squared from each term here. We sum them together, so we get just 1 divided by minus psi squared. So the square of the amplitude is just y to the 4 divided by m psi to the 4. And remember that this has mass dimension 1, so the whole mass dimension of this amplitude here is 0, as it should be. So now when we write down the expression for the cross section, first the ratio of those final and initial momentum. The final momentum we said is m psi. The initial momentum is m psi times v. We said it's small, but now we can't really take it to exactly 0 yet, because otherwise the quantity would diverge. So we get 1 divided by the relative velocity of the initial particles from this term. We get the usual term here, and we get a factor. We have to include a factor of 1/2, which avoids double counting for identical particles. This is a rule that we have to, if we have 2 identical particles in the final state, or 3, or any number of identical particles in the final state, we have to divide by this number. Otherwise, the momentum, the phase space integrals would lead to double counting. Well, now A here again, as you see, is theta independent. We have the integral over the solid angle just gives us 4 pi. And so the total annihilation cross section is given by 1 divided by 128 pi divided by 1 psi over psi squared. This ratio, this is a dimensionless number, 1 divided by the relative velocity. Good. Let us now define the dimensionless coupling that we call y squared divided by m psi squared. This is a dimensionless number that measures the strength of the interaction of the theory, and it's conventional to divide by 4 pi. This is the analogy for alpha electromagnetic in quantum field theory is the electric charge squared divided by 4 pi. And so the annihilation cross section becomes quite simple. So it's just pi alpha squared divided by 4m psi squared times v rel. And it's very similar to the annihilation of the plus or minus, which is has a factor of 4, is factor of 4 larger. Otherwise, it looks the same as from the structure. Now, it's interesting that it seems divergent when the relative velocity goes to 0. However, this is not a physical observable yet, really. What we observe are the annihilation rates. And now consider also the flux of incoming particles, like, for example, the flux of psi bar, it's v rel times the number density of psi bar, right? And psi bar is then, n psi bar is the number of particles per volume. And they interact with a population of psi, which have relative number density of n psi divided by volume. So their annihilation rate per volume is the annihilation cross-section times the flux times the number and density of psi. And accordingly, the annihilation rate per particle psi, the probability for each particle psi to get annihilated is this annihilation rate per volume divided by number density of psi's, which is sigma annihilation times the VREL from the flux here. We plug in VREL times number density of psi bars, and that cancels this V bar that was in the VREL that was in the denominator here in the cross section. This is gone. So we have a cross section that is annihilation rate that is given by pi alpha squared divided by 4m psi squared times the number density of psi bar. And this quantity is often called sigma naught, the leading order expression for this annihilation. And it's just the sigma naught times psi bar. And you see that it is finite even if the velocity goes to 0. We also see that it's a mass dimension is 1, as it should be, because this is a rate, right? The rate is an annihilation per time. It's inverse length, so it has to have the same as mass dimension as mass dimension 1. Remember again, this is an area, right? So this is an area, so it's 1 over length squared. So it has to have mass dimension 2. And this is 1 divided by volume, right? This is 1 divided by volume. So it's 1 divided by length cubed. So this is just the mass dimension minus 3. And minus 3 plus, it has mass dimension exactly 3. And this has mass dimension minus 2 because it's length. This is length squared, as we said. Area length squared has mass dimension 2, and this has mass dimension, minus 2, and this has mass dimension 3. So overall, this combination has a mass dimension of 1. Good. Now have a look at the application in high energy astrophysics. For example, you have psi bar annihilating to gamma gamma, for example. Yeah, we didn't talk about photons yet, really, but as I said, it's annihilation of two particles that carry charge to massless particles. And you can imagine that this is a model of dark matter that has some sort of dark charge. It doesn't have electric charge, obviously, but it has a charge on its own. So we have a conservation of quantum numbers in the dark sector that has these hypothetical particles that can annihilate to photons. So the expected photon count rate, if we have a telescope that points at a certain region in a galaxy, we have to take a line of sight integral of this volume reaction rate, annihilation rate. We assume, by the way, that the number densities of psi's and psi bars of those new particles, dark matter particles, are equal, and I can justify it later. Essentially it comes from the production mechanism of the particles in the early universe. But let's just assume it for now. So this sigma annihilation times VREL is sigma naught, as we said. These brackets correspond to velocity average. However, as we saw, the leading term is independent of velocity, so the velocity average is just the number itself. And then we have number density squared. We write as the density squared divided by the mass squared, such that we have here all the parameters that are described by particle physics models. And independently here we have the density, the physical density of the dark matter particles squared that we integrate over the line of sight. And this is an astrophysical this is an astrophysical parameter because the density of the dark matter particles we know from gravitational potentials that we can extract from stellar motion, for example. So we have an ingredient that comes from the astrophysics, we have a hypothesis about particle physics, and now we can have an expected rate in our detectors. For example, the Fermi Large Area Telescope, that is a satellite experiment, looks at gamma rays, it looks at the galactic center. The galactic center is about 8 kiloparsecs, which is maybe like 15,000 light years away from us. We can look at the galactic centers where it should have a very large abundance of dark matter in terms of that we know from stellar motion. And looking at this, we can define a region, look at a certain area, and compare our expectations with what we observe. Of course, one has to take out all the backgrounds, that means all the shining sources in the galaxy to do this analysis, but let's say it can be done. And what the situation is now is, apart from an inconclusive excess, actually around about 10 gigaelectron volts, um, we don't see a conclusive signal yet. So what we can do for certainty is exclude a certain range of this annihilation cross sections. And there's the experiment for, so in this plane of cross section on this y-axis, and as a function of the dark matter mass of the x-axis, the Fermi experiment excludes a certain range of large cross sections. It has better sensitivity to lower dark matter masses because number densities are expected higher, and then the rate here is expected to be larger. So yes, we have these limits that go like this. From the Fermi experiment, there's another Cherenkov telescope array that looks for even higher energy cosmic ray interactions in the atmosphere that can be also induced by high energy photons from dark matter annihilation. That excludes very large cross sections at large masses. But the interesting target cross section is actually 10 to the minus 26 in physical units, centimeters cubed per second. And that has to do with the production mechanism in the early universe that we could discuss at some point. That the so-called freeze-out production predicts a certain annihilation rate that is needed to explain the abundance of dark matter, and this is a target for experiments to look for. So this Fermi satellite has essentially reached the target around 10 GeV. Depends on the annihilation final channel. Here, for example, I drew this line that many very common analysis of the annihilation of these particles into B quarks. But in the end of the day, the limits will be quite similar, and depending on the final state, range between 10 and 100 gigaelectron volts. And yeah, so the goal in this case is actually to push with better sensitivity to higher masses in this dark matter range to test even heavier dark matter scenarios. Well, and yeah, there are also general considerations that think that 100 TeV here is a natural barrier that thermal dark matter annihilating to a 2 to 2 through a 2 to 2 interaction should not exceed. There are quite reasonable arguments for that. So this parameter space here is really interesting and is being currently tested. So we are actually testing a very broad and important range of models by improving the so-called Cherenkov telescope technologies that will actually advance on this parameter space here. So that's the exciting part on the experimental side. Well, that's it for today, and for in the next lectures we will look at so-called processes, loop processes that are needed for renormalization and regularization, that need regularization and renormalization in order to make sense of higher order diagrams in quantum field theory.